Welcome to today's lecture on the crystal structure of solids. This topic is fundamental in understanding the behavior of materials, especially in semiconductor technology. We will explore the atomic arrangements of solids, their classifications, and the role of crystal structures in defining material properties. The crystal structure of solids is more than just an arrangement of atoms. It determines fundamental physical properties such as electronic band structure, charge carrier mobility, and thermal conductivity. The type of bonding and atomic arrangement in a crystal influences its electrical properties. For example, in a diamond cubic structure like silicon, each atom forms 4 covalent bonds, creating a stable but indirect band gap that makes it ideal for microelectronics. Crystals can also be classified based on their Bravais lattices, of which there are 14 unique types categorized into 7 crystal systems: cubic, tetragonal, orthorhombic, monoclinic, triclinic, hexagonal, and rhombohedral. Each lattice type defines unique symmetry and material properties. Additionally, crystal defects such as vacancies, interstitials, and dislocations play a crucial role in modifying electrical and mechanical properties. By carefully engineering these defects, scientists can enhance semiconductor performance or create materials with specific desired characteristics. Semiconductors can be classified into elemental and compound types. Silicon, a group 4 elemental semiconductor, forms a diamond cubic crystal structure, making it ideal for stable electronic applications. Germanium, another group 4 element, has similar properties but higher carrier mobility. Compound semiconductors, such as gallium arsenide, GaAs, have a zinc blende crystal structure, offering a direct bandgap suitable for optoelectronics. Ternary and quaternary compounds like AlGaAs and NGSP provide tunable electronic and optical properties by varying their elemental composition, enabling advanced applications in photodetectors, lasers, and high-frequency transistors. Solids are classified based on their atomic arrangement. Amorphous solids, like glass, have no long-range order, meaning their atomic structure is randomly distributed without periodicity. This randomness results in poor electrical conductivity, making amorphous materials useful for insulating applications. Polycrystalline solids, such as metals and some ceramics, contain multiple small crystalline regions called grains. The grain boundaries can scatter electrons and phonons, affecting electrical and thermal conductivity. Single crystal materials used in semiconductor wafers have a continuous and defect-free periodic atomic arrangement, which enhances carrier mobility and reduces electron scattering, making them ideal for high-performance electronic and optoelectronic devices. A crystal lattice is a periodic and highly ordered arrangement of atoms in 3 dimensions, which plays a crucial role in defining the physical and chemical properties of materials. The unit cell, the smallest repeating structural unit, dictates the symmetry and properties of the crystal. Translation vectors in 3 non-collinear directions define the periodicity and determine the repeating pattern of the lattice. The translational symmetry of the lattice results in unique electronic band structures, leading to the formation of energy bands and gaps, which are fundamental to the electrical and optical properties of semiconductors and other materials. Understanding the structural order allows for precise tailoring of materials used in semiconductors, superconductors, and photonic devices. Crystals adopt different structures based on atomic arrangements, which influence their packing efficiency, density, and mechanical strength. The simple cubic structure has atoms only at the corners, resulting in a low packing efficiency of about 52%. The body-centered cubic BCC structure has an additional atom in the center, increasing packing efficiency to about 68% and improving mechanical strength, making it common in metals like iron and tungsten. The face-centered cubic FCC structure, with atoms on each face, achieves a packing efficiency of 74%, providing high ductility and electrical conductivity, as seen in metals like copper, aluminum, and gold. These structural differences determine how materials respond to external forces, thermal expansion, and electronic properties. Miller indices are essential in describing and categorizing crystal planes, which are crucial in understanding anisotropic properties of materials. These indices are derived by determining the intercepts of a plane along the crystal's lattice vectors, taking their reciprocals and clearing fractions to get integer values. For example, consider a plane that intersects the x-axis at 2a, the y-axis at 3a, and the z-axis at 1a. First, we take the intercepts 2, 3, 1, then take their reciprocals 1/2, 1/3, 1, and clear fractions by multiplying by the least common multiple, which is 6, yielding 3, 2, 6. Thus, the Miller indices for this plane are 3, 2, 6. This notation is widely used in analyzing diffraction patterns in X-ray crystallography and electron microscopy, both of which are fundamental in materials characterization. Furthermore, Miller indices help predict the behavior of etching, growth patterns in semiconductor wafers, and cleavage planes that determine mechanical stability in crystal structures. Crystal directions describe how atoms are aligned in a material. These directions are particularly important in understanding anisotropic properties, how material behaves differently depending on the direction of applied stress, electric fields, or thermal gradients. For example, in a simple cubic lattice, the 100 direction runs along an axis, while 111 represents a diagonal path through the unit cell. In materials science, understanding crystal directions is crucial for optimizing the mechanical properties of metals and alloys, as well as for tuning electronic band structures in semiconductors. For instance, the mobility of charge carriers in silicon varies along different crystal directions, influencing the design and efficiency of semiconductor devices. Crystal growth techniques impact the purity and performance of semiconductors. The Czochralski method is widely used for growing large silicon wafers by slowly pulling a single crystal seed from molten silicon. The float zone method, on the other hand, eliminates impurities by using a moving heat zone, leading to extremely high purity silicon used in high-performance electronics. For compound semiconductors, molecular beam epitaxy (MBE) allows for precise atomic layer deposition in an ultra-high vacuum, enabling the growth of complex heterostructures. These methods are essential in fabricating transistors, LEDs, and photovoltaic cells, where material quality determines efficiency and reliability. Crystal structure plays a vital role in semiconductor fabrication. Proper wafer orientation ensures efficient transistor operation, while crystal planes influence lithography and etching techniques. For example, the 100 plane in silicon provides better doping uniformity and oxidation characteristics, making it the preferred orientation for CMOS technology. The surface properties of different crystal planes also affect device performance. For instance, GaAs-based LEDs and lasers rely on well-defined crystal orientations to optimize optical output. Similarly, high electron mobility transistors, HEMTs, leverage specific orientations to enhance carrier transport properties. Understanding these interactions between crystal structures and device fabrication is key to advancing modern semiconductor technologies. To summarize, the crystal structure of solids is a fundamental concept in materials science. It determines the electrical, optical, and mechanical properties of materials. Semiconductor devices depend on precise crystal structures, making this knowledge crucial for advancing technology. From Miller indices and crystal planes that dictate surface behavior to the sophisticated growth techniques ensuring material purity, every aspect of crystallography contributes to the design and performance of electronic and optoelectronic devices. As technology progresses, a deeper understanding of these principles will enable further breakthroughs in nanotechnology, quantum computing, and advanced semiconductor applications.